Start. Okay. So our next speaker is Sanchayan Sen. Sanchayan did his PhD from NYU, and after that he was postdocs at Eindhoven and McGill University. And then he joined ISC. He's an assistant professor there, and his research interest lies in random graph, random network, complex network scaling limits. And Sanchayan is going to talk on new universality classes for minimal spanning trees. Sanchayan, over to you.
Thank you. And also thanks to the organizers for arranging this meeting. So today I want to talk about joint work with Shankar Bhamidi, where we study the scaling limit of minimal spanning trees on heavy tail random graphs. So first of all, what is a spanning tree? Suppose G is a finite connected graph with vertex at B. Then a spanning tree of G is a tree that is a subgraph of G, and it goes through all the vertices. So this would be an example of a graph G, and then on the right, this is a spanning tree of G. Okay. Now we'll study the example of random spanning trees is that of the uniform spanning tree. So uniform spanning tree means you're given a finite connected graph, and you look at the set of all spanning trees of that graph, and you pick one uniform. Minimal spanning trees are actually different from uniform spanning trees in the sense that asymptotically they exhibit different behavior and that they belong to different universality classes than uniform spanning trees. So I'll come back to this point later. Now here's the definition of the minimal spanning tree. So as before, let's say you have a finite connected graph G, but now your edges are weighted. So you have a weight function B, a non-negative weight function B on the edges, then a minimal spanning tree of G minimizes the total weight over all spanning trees T of G. So for any spanning tree of the graph G, you can compute its total weight, and a minimal spanning tree minimizes that total weight. And it's also easy to see that the minimal spanning tree is unique if the edge weights are pairwise distinct. Okay, this follows from a standard property of minimal spanning trees. So in particular, if the edge weights are, let's say, IID uniform 0-1 random variables, then it makes perfect sense to say the minimal spanning tree, because with probability 1, all the edge weights are pairwise distinct, and there is a unique minimal spanning tree there. Now, minimal spanning trees have been studied extensively in probability and combinatorial optimization. And you can study them in many different settings. So these are the two standard settings where you can consider minimal spanning trees. One is when the underlying graph is either deterministic, for example, it's the complete graph on n vertices, or maybe it's the hypergraph with 2 to the n vertices, the hypercube with 2 to the n vertices, or the underlying graph could also be random. For example, it could be the erosion random graph or the random 3-regular graph. And typically in these situations, the edge weights are taken to be IID random variables, like IID uniform 0-1, for example, or IID exponential. There's a second setting where the underlying graph is a random geometric graph. Here, the vertices are the points of some point process. Could be a Boswell point process, or let's say in IID points with some density in some bounded region of RD. And here, typically, the edge weights are functions of the edge lengths. Now, in this talk, we'll be focusing on this first setting. And there's a vast literature on the study of random minimal spanning trees. There are many results on the total weight of minimal spanning trees, law of large numbers, central limit theorems, results of that nature. But there aren't too many rigorous results on the global geometry of minimal spanning trees. So, for example, what is the order of the diameter? Or what is the order of the typical distance? And more generally, what does the entire minimal spanning tree look like if you view it as a matrix space? So that's what we're going to talk about in this talk. Now, there's another way of arriving at minimal spanning trees, and this comes from the study of disordered networks. So suppose you have a finite connected graph G, and to each edge in the graph, you assign a cost exponential beta epsilon E. To each edge E, you assign a cost like this, where the epsilon e's are pairwise distinct. Then the total cost of a path in the graph is just the sum of the costs along the edges. And it's easy to see that when beta is sufficiently large, then the dominant contribution in that sum comes from the maximal edge weight, the edge with the maximal cost. So if you have two vertices in the graph, then the path in the graph connecting those two vertices that minimizes the total cost is also the path that minimizes the maximal edge weight among all paths connecting those two vertices. Okay, now this is also the path that connects those two vertices in the minimal spanning tree of G constructed using the same edge weights. This is also very easy to prove. It's just a standard property of minimal spanning trees. So in other words, in the presence of strong disorder in a network, the optimal path in the network is also the path in the minimal spanning tree on that network. Okay. Now, scaling of distances in the strong disorder regime in random networks was studied through simulations in the early 2000s in the statistical physics literature, and there are many papers in this direction. And what it was predicted that if you have a scale-free random network on n vertices with degree exponent tau bigger than 3, then the typical distance in the presence of strong disorder, so this L opt, this scales like n to the 1/3 if tau is bigger than 4, and this scales like this n to the tau minus 3 over tau minus 1 if tau is between 3 and 4. Now, the exact definition of the scale-free random graph and the degree exponent will not be relevant in this talk, so I'm not defining it properly. So it's just something to point out here that you have two distinctly different regimes here. So when tau is bigger than 4, then the typical distance scales like n to the 1/3, and this is basically where you expect mean field behavior. And for every value of tau between 3 and 4, the typical distance is expected to scale like n to the tau minus 3 over tau minus 1. So for each tau between 3 and 4, you're expected to see a different universality class, right? And another thing is that all these exponents are, so none of them equal 1/2. So in many standard models, it's known that the uniform spanning tree scales like the distance, the typical distance of the diameter of the uniform spanning tree scales like square root of n. So this is known for example, the uniform spanning tree of a complete graph, which is the uniform label tree. This is also known for several other models, that the typical distance in the uniform spanning tree is of the order of the number of vertices to the 1/2. But the minimal spanning tree, just by looking at these exponents, one can guess that you should expect a different kind of behavior for minimal spanning trees. And if the scaling limit of these minimal spanning trees exists, then they would typically be in a different universality class. Okay. Now here are some known results on minimal spanning trees, on distances in minimal spanning trees for models that exhibit mean field behavior, right? So in this paper by Adderioberry, Bruton, and Reed, this is an RSA, they showed that if you look at the complete graph and you assign IID uniform edge weights, let's say, and you look at the minimal spanning tree, call it Mn complete, then its diameter is big OP of n to the 1/3. So this is a probabilistic upper bound on the diameter. And Nakmias and Perez in this paper showed that if you look at the largest component of the critical erosionary random graph, then its diameter scales like n to the 1/3. Now there's a very simple coupling between minimal spanning trees and percolation, and using that you can easily conclude from this result by Nakmias and Perez that the diameter of the minimal spanning tree of the complete graph is actually lower bounded by n to the 1/3 probabilistically. So you can combine these two results to conclude that in fact the diameter of the complete graph on n vertices, it is exactly of the order n to the 1/3, it's theta p of n to the 1/3. Then a more general result was proved in this paper by Adderioberry, Bruton, Goldschmidt, and Miermont relatively recently, Here, they obtain the full scaling limit of the MST of the complete graph. So what they showed is that if you look at the complete graph on n vertices, assign IID uniform 0, 1 weights to the edges, and you construct the minimal spanning tree, then you think of the minimal spanning tree as a metric measure space. Now, on any tree, there's a natural tree distance. You can use that tree distance to think of the tree as a matrix space. In addition, you can endow the tree with the uniform probability measure on the vertices. That will turn the tree into a metric measure space. Now, if you look at that metric measure space, and if you the metric measure space that you get from the minimal spanning tree, and you scale the distances by n to the minus 1/3, then what they proved in this paper is that that metric measure space converges in distribution to a limiting random fractal with respect to the Gromov Hausdorff of topology. And they further showed that this limiting space M, this limiting fractal, this is almost surely compact. This is a binary real tree, and its Minkowski dimension is 3. Okay. Now, more recently, in a joint work with Luigi Adoraberi, we were able to show that this is also the case for 3 regular graphs. So if you look at the simple random 3 regular graph or the 3 regular configuration model, and you construct the minimal spanning tree on the 3 regular configuration model or the simple random 3 regular graph, think of it as a metric measure space just by the same prescription that I described earlier, and you scale the distances by n to the 1/3. Then this too converges to a limiting random fractal, and in fact, this time the scaling limit is just the scaling limit that you get for the complete graph up to a constant multiplicative factor of 6 to the 1/3. And we were also able to show that the mass measure on this limit is actually non-atomic almost surely. Now, these are all the results that are known about the scaling limits of the minimal spanning tree. Note that both these models, they exhibit mean field behavior. So both of them, they fall in this regime. But the tau between 3, 4 regime, this regime was completely open, and the prediction was not rigorously proved for any model in this regime. And that's the purpose of this work, is to introduce the scaling limit in this regime.
Sorry,
yeah.
Can I ask a quick question?
Please.
So for this random 3 regular graphs, I mean, for the complete graphs, it's kind of obvious that it's a mean field model, but this random 3 regular graphs is not obvious, right? That it should be a mean field kind of result? Or is that obvious from some other intuition?
So there are several results known about the nature of phase transition on random regular graphs. And it's known that the size of the largest component is like n to the 2/3 in the critical window. And also the critical scaling limit. If you do critical percolation on random regular graphs, then the scaling limit, the matrix scaling limit, is also known and is of an Erdős type. So that those results actually have been proved.
Okay. So
also, if you think of the statistical physics, if you want to connect it to the statistical physics literature, then this kind of result should also hold when tau equals infinity. So tau equals infinity corresponds to a degree distribution in the graph that decays faster than any polynomial. And for random regular graphs, the degree is bounded. The degree distribution is bounded. It's just delta at a single point. So from that also you expect this Erdős kind behavior here, right?
I see. Okay, thanks.
But may I ask, Sanchayan, why 3? I mean, could you prove it only for 3 and not general D? Is there something?
Now, this proof only worked for 3. The reason is, if you look at the critical Erdős random graph, then inside the critical window, the core of the largest component, let's say, it's distributed as a 3 regular configuration model conditioned to be connected. So there's a coupling between the 3 regular graph, the 3 regular configuration model, and the Erdős process.
I see.
And that's the one we use to prove this.
Okay.
But that does not work for a general R regular graph. So that has to be done in a slightly different way. Okay, so the purpose of this talk is to study the behavior of the MST in the tau between 3 and 4 regime. So this is the model. that we're going to consider. So we'll have n vertices labeled 1, 2, n. In addition, let's say we have vertex weights, W1, W2, that are ordered like this. And what you do is you place edges independently between I and j with respective probabilities, either this or this. You can take either one because the regime where we'll be working, these two are actually equivalent in the sense that if you look at the random graph model where the connection probabilities are this, and you prove something, then those results are automatically translated to the other random graph where you have, or the connection probability is this one. So you can consider either of these connection probabilities. Now in the rank one, in the random graph literature, this is often referred to as the rank one inhomogeneous random graph. But it's also the random graph associated with the multiplicative coalescent at a fixed time. The multiplicative coalescent is a stochastic process that was introduced by Aldous in the late 90s and was further studied by Aldous and Lemech. And the multiplicative coalescent is usually expressed in a slightly different way. The parametrization is a little different, but the way the random graph I've written here, this is just basically the same random graph, but it's just parameterized in a slightly different way. And because of this connection with the multiplicative coalescent, this model is a special one. And the multiplicative coalescent, the scaling limit that you get for the multiplicative coalescent is expected to be universal for a large class of models. So something similar should be true for the minimum spanning tree. And the scaling limit of the minimum spanning tree for this model that we obtain in our result is also the candidate for the universal minimum spanning tree scaling limit in the heavy-tailed regime for a wide array of random graph, heavy-tailed random graph models. Right, so this is one specific model, but this is a special model because of the connection with the multiplicative coalescent. Now, these are the assumptions on the WIs that we need. So you fix a tau between 3 and 4, and you define two exponents alpha and eta like this. Then we assume that we have a sequence of weight sequences that satisfy these four assumptions. This first assumption is needed. This just ensures that the random graph model is supercritical. Okay, so you need supercriticality for the scaling limit of the MST to turn out the way we want it to. The second condition was introduced and studied by Aldous and Lemech in their late 90s paper. Now, again, in the multiplicative coalescent, things are parameterized in a slightly different way, but if you translate that using this notation of WI, then this Aldous-Lemech condition from their paper in terms of WIs is exactly this. So this shows that basically for any fixed I, the ith largest weight with appropriate scaling converges to a limit theta I star. Now, in addition, we need two other conditions. The third condition says that for the larger values of I, for I bigger than, for I between 1 and n over 2, WIN is equivalent to n over I to the alpha up to a certain constant, up to constants. And we also need a lower bound on the minimum weight. We can't have the minimum weight too small. Now, these are some general assumptions, but these are some general assumptions, some general conditions on the weights, but you can, there's a standard way of generating weights that satisfy these assumptions, either deterministically or almost surely. So suppose you have a CDF, a cumulative distribution function supported on the non-negative real line that satisfies these three conditions. The third condition basically just ensures that the random graph model is supercritical. This condition in the middle, this will make sure that the Aldous-Lemech condition is true. And also the third condition that I mentioned in the previous slide, that's true. And this first condition makes sure that the minimum weight, the condition on the minimum weight is satisfied. So for any CDF like this, if you look at NIID random variables that follow this distribution and you order them, then these weights satisfy these conditions that I stated in the previous slide. These conditions are satisfied almost surely by these weights, these IID weights. You could also instead look at the quantiles of such a distribution F, then these weights will also satisfy those conditions deterministically. Okay. Now, under these assumptions, now here's the result here's the main result of our paper. So you look at that random graph model that we defined earlier, and assume that the weight sequence satisfies those conditions. Then you assign IID uniform weights to the edges of this random graph, and you look at the component of the vertex 1, and you look at the MST Mn of the component of the vertex 1. Now, here under these assumptions, you can actually show that with probability tending to 1, the mass of the largest component will be the largest. The mass of the largest component would be same as the mass of the component of 1. In other words, the component of the vertex 1 will have the largest mass, with probability tending to 1. So we're looking at the component of the vertex 1, but you could also look at the giant, because it's just the component of the vertex 1 with probability tending to 1. Now then, in this setting, this is our main theorem. This says that you have this MST, Mn. Now think of this as a matrix space using the tree distance. Then if you scale the distance by n to the eta in this random matrix space Mn, then this random matrix space converges in distribution with respect to the Gromov-Hausdorff topology to a limiting random compact matrix space, this M theta star, whose law depends only on this sequence theta I star. So this sequence theta I star was specified in the conditions on the weight sequence. There is a limiting random compact matrix space M theta star. That is the scaling limit of these sequence of random matrix spaces into the eta over Mn. Now, this in particular implies that the diameter of the tree Mn scales like n to the eta. So this gives some rigorous justification for the conjecture that came from statistical physics literature. Remember this eta was just tau minus 3 over tau minus 1, which was exactly the predicted scaling of distances for the minimum spanning tree in this regime. Now, we also study some topological properties of this limiting space M theta star. We show that almost surely every point in this limiting space either has degree 1 or 2 or infinity. Now, points with degree 1 are referred to as leaves, and points with degree infinity, we call them hubs. And almost surely the set of leaves and the set of hubs are dense in this limiting space M theta star. And finally, the Minkowski dimension of this limiting space M theta star is almost surely tau minus 1 over tau minus 3. So note that these topological properties of this M theta star are markedly different from the scaling limit that I talked about earlier in the mean field regime. In the mean field regime, the scaling limit of the MST was a binary real tree, whereas here the degrees can be infinity. It's in fact 1, 2, or infinity. Also, the Minkowski dimension here is tau minus 1 over tau minus 3, whereas there it was 3. So these trees are in fact fatter compared to the mean field scaling limit. And in fact, I have two simulations. The one on the left is this is a simulation of the minimum spanning tree in this model for tau equal to 3.05, and on the right, this is a simulation of the MST for tau equal to 3.95. And note that the tree on the left is noticeably fatter, and that's to be expected because as tau approaches 4 from the left, the trees are expected to get thinner. Okay, I will briefly go over the proof ingredients. I'll just explain the ideas in words. Now, the proof requires careful control on the graph in the so-called critical window. So consider bond percolation on this random graph with edge retention probability Cn times 1 plus lambda over n to the eta, where lambda is positive, and the Cn is chosen in a way so that the graph is in the critical window. Then we look at this graph after percolation, and we consider a version of the breadth first walk on this graph. And we prove a concentration inequality on the supremum of the centered breadth-first walk using a Klein-Rio bound. Now, using this concentration inequality, you can prove various tail bounds on different quantities associated with the component of the vertex 1. In particular, you can show that the sum of Wj squared, sum taken over all j in the component of 1, is lower bounded by something with high probability. Now, remember that in the conditions, I had a parameter something like sum of Wj squared over sum of Wj. This corresponds to the criticality or subcriticality or supercriticality parameter of the graph. Now, if you could show that a large chunk of sum of Wj square is contained in the component of 1, then you can use that to show that in fact the rest of the graph is subcritical. So using this, we can actually show that the outside of the, if you look at the complement of the vertex, the component of the vertex 1, then that graph is in fact subcritical in a suitable sense. Now you also need the diameter bound on the complement of the component of the vertex 1 to make the proof work. Now to do this, we stochastically upper bound the component of any vertex by a 3-layer branching process. And then we obtain tail bounds on the heights of such branching process. So when I say 3-layer branching process, this here we consider a branching process where at different stages, there are 3 stages, and in those 3 stages, the branching process has different offspring distributions. Now, the age retention probability here is 1 plus lambda over n to the eta times a constant. This makes the graph critical in the sense that it's in the critical window, but it's also slightly supercritical because this lambda is positive. Now, here we choose, in this 3-layer branching process, we choose the offspring distribution in the first layer in a way so that it counteracts the effect of this slight supercriticality coming from this age retention probability. Now, and in the second layer, we choose the offspring distribution in a way so that in the end, when you do something like a union bound, then that series becomes summable. And in the third layer, we actually need a height bound on a branching process, a bound of the form 1 over n to the eta. This is also needed to make the bound work. And for this third layer, key ingredient in the proof is a technique that was recently introduced by Luigi Adderberry in this 2019 paper. This is a very this is a very useful technique that can be adapted to many random graph models. And building on Luigi's technique, we're able to get the tail bound on the height in the branching process in the third layer. Now I'll quickly run through the rest of the argument. And now once you have this diameter bound, you can combine them with the results on critical scaling limit of the graph that was obtained in one of our previous works. Now that plus some additional work would yield the existence of the scaling limit m theta star. Now there were several other claims about the topological properties of this space m theta star. Now the claims about the degrees of points in the scaling limit, they can be proved using properties of the critical scaling limit, which can be constructed in terms of ICRTs, these inhomogeneous continuum random trees. So using properties of these inhomogeneous continuum random trees, you can prove the claims about the degrees of these points in the scaling limit. And finally, the proof of the Minkowski bound uses discrete approximation. Now, this is my last slide. And here I want to say a few words about the universality of the scaling limit. So as I mentioned earlier, that this model is basically just a reparameterization of the random graph associated with the multiplicative coalescent. And in our one of our previous works, we showed that for many different random graph models, if you look at the random graph inside the critical window, then they can be coupled with the multiplicative coalescent in a very nice way. And the scaling limits that you get for the random graphs associated with the multiplicative coalescent also arise as a result of this coupling. You can show that they also arise as a scaling limit of all these random graph models, right? And something similar should be true here for minimum spanning trees. So we already have the scaling limit for the multiplicative coalescent for the MST constructed on the random graph associated with the multiplicative coalescent. Now this same MST should be the scaling limit construct of the MST construct on the giant component of several other different models with heavy tail degrees. In the two most important models are these two. So the first one is the supercritical simple random graph with heavy tail degree sequence, or the multi-graph configuration model with a heavy tail degree sequence. And the second one is where you look at a sequence of dense graphs that converge to an LP graphon, where P is between 2 and 3. Now for the second model, Bolobash, Borgs, Chase, and Riordan studied the phase transition in such dense graphs, but they only consider the case L infinity. They only consider the case of L infinity graphons. And we currently have a paper in preparation where we study the sequence of dense graphs converging to an LP graphon where P is bigger than 3, and we look at the phase transition in these graphs, and we actually get the critical scaling limit for such graphs. But this result, first of all, it only deals with the critical window, and it only deals with models where P is bigger than 3, where you are expected to see mean field behavior. But this problem is open in the P between 2 and 3 regime, and this is where we expect that the both the critical scaling limit and the MST should be the one that we get for the for the scaling limit that we get for the multiplicative coalescent, and in particular this model should be in the same universality class. I think I'm going to stop here, and thank you very much for your attention.
Okay, thank you, Sanchayan, for an interesting talk. Any question, comments?
One question. So Sanchayan, so about these points of infinite degree in this limit. So you said they are dense, right? So is that right?
They're dense, yes. They're almost surely dense in the space, yes.
Okay, so it doesn't make sense to ask for dimension or any such thing, or is it more in as tau becomes closer to 3? I mean, is that correct or not?
So the hubs they're expected to be thicker as tau approaches 3 from the right, yes. But we don't have a quantitative result for that.
Yeah, but I mean, can we talk about the dimension of it if it's
so
not
the dimension of the hubs in the space?
Yeah, I mean, maybe that it is a dense set, you said. I don't know if it makes sense or not.
It's a dense set, but there are only countably many.
Countably many. Oh, okay. I see. Okay.
So these are basically the branch points.
Okay, thanks.
Any other question?
Just one question. Sanchayan, you said that both are dense, right? Leaves are dense?
Yes.
Oh, both are dense. I see.
Yeah, but there are uncountably many leaves, but only countably many branch points, hubs.
I see. Countable many hubs. And how many are those of degree 2?
Those are also uncountable. So degree 2 are basically, so let's say if you imagine a combinatorial tree, degree 2 is just the points in between that are not,
right. Correct.
Are not branch points or leaves. So yeah, there are many of those. Yes.
Okay. Oh, I see.
It's just the points in between. It's like
yeah. Right.
Yeah.
Okay.
Yeah.
Right.
Okay. Anyone else wants to ask questions? If not, let's thank Sanchayan again for this interesting talk. Okay, so next talk will be at 4:50, I guess. Bill 2 is the next speaker.